Welcome to Wood Science. Hexagonal Boron Nitride Nanosheets as high-performance binder-free fire-resistant wood coatings. Wood is a versatile material widely employed in construction, furniture, and panels. The research focus on fire-resistant wood coatings emphasizes properties like fire resistance, hydrophobicity, UV protection, durability, toughness, and oxidation resistance. Wood coatings are classified into binder-free and binder-combined categories. Typical wood coating components include binders, fillers, pigments, flatting agents, solvents, and additives. Common wood coatings include wax, shellac, nitrocellulose lacquer, varnish, linseed oil, polyurethane, and epoxy resins. Polyurethane coatings stand out for their high gloss, flexibility, and chemical resistance. Fire-retardant coatings utilize additives like borax, boric acid, antimony trioxide, and chlorinated compounds to inhibit combustion. These fire-retardant coatings often require additional binding materials that may be toxic and susceptible to mechanical instability due to corrosion, cracking, and environmental factors. The search for a binder-free material with intrinsic fire-retardant properties is crucial for wood coatings. Hexagonal Boron Nitride, HBN, is a thermally and chemically resistant compound of boron and nitrogen, isoelectronic to graphene. Hexagonal boron nitride is recognized for its effectiveness in fire-resistant coatings for metal and metal oxide surfaces. A hexagonal boron nitride or polymer coating demonstrates efficient corrosion protection, characterized by a low corrosion current density, 514 by 10 to the power negative, a centimeters to the power negative 2, and a corrosion rate, 119 by 10 to the power negative 3 mm per year. This effectiveness is attributed to hexagonal boron nitride's hydrophobic, chemically inert, and dielectric nature. Hexagonal boron nitride exhibits oxidation resistance up to 1,000 degrees Celsius in air, making it a robust choice for high-temperature applications. While the use of boron nitride as an impermeable coating has been reported for various substrates, the application of hexagonal boron nitride for wood protection coatings is a novel and unexplored area. Liquid phase exfoliation of hexagonal boron nitride nanosheets and wood coating. In a typical liquid phase exfoliation, approximately 4 grams of bulk boron nitride (BN) powder is dispersed in a prepared sodium dodecyl benzene sulfonate (SDBS) or water suspension, 100 milliliters volume, with a fixed SDBS concentration of 1 milligram per milliliter. The boron nitride, sodium dodecyl benzene sulfonate, SDBS, and water dispersion undergoes probe sonication for 4 hours with 3 seconds on and 3 seconds off intervals using 50% amplitude. An ice bath is maintained to suppress heat. After sonication, the suspension is left overnight, and the top 80% supernatant is collected and centrifuged at 1,500 revolutions per minute for 90 minutes. The top 60% supernatant is then collected, and the sediment is discarded, resulting in a semi-transparent boron nitride nanosheet suspension. To achieve high concentration, a high-speed centrifugation process is employed. The stock boron nitride, BN, nanosheets dispersion is subjected to 15,000 revolutions per minute, RPM, for 20 minutes, discarding the top 90% supernatant and collecting the sediment. Similar exfoliation is performed with boron nitride powder in isopropyl alcohol, IPA solvent, maintaining a 20% amplitude to prevent rapid solvent evaporation. Wood substrates, specifically cedar trees, Cunninghamia lanceolata, are used for surface exploration. Optical microscopy reveals a high degree of surface roughness in pristine wood, Figure 1b. Coating with hexagonal boron nitride, HBN, nanosheets results in a smooth surface as shown in magnified images, Figure 1CD. Structural and elemental characterization of hexagonal boron nitride, HBN, nanosheets. Elemental composition of exfoliated hexagonal boron nitride nanosheets was analyzed using Raman spectroscopy. Raman spectra revealed an intense peak at 1365.8 centimeters to power negative 1, corresponding to the E2G vibration mode of hexagonal boron nitride, HBN. The FWHM of this mode was 521 cm1, indicating high-quality hexagonal boron nitride HBN nanosheets. Changes in the E2G vibration mode intensity were linked to reduced interlayer interaction during the exfoliation of boron nitride BN powder. Raman spectra of boron nitride, coated wood substrate after 1 minute and 5 minutes of exposure to fire were presented in supporting information. Structural integrity and crystalline ordering of boron nitride BN nanosheets were examined using X-ray diffraction analysis. The presence of the characteristic Bragg reflection plane at a tooth value of 26.5 degree confirmed the hexagonal boron nitride HBN, aligning with literature reports. The elemental composition of boron nitride BN nanosheets was further investigated through X-ray photoelectron spectroscopy XPS, and results were compiled in supporting information. Mesoscale surface morphology was investigated using scanning electron microscopy SEM. Scanning electron microscopy SEM results illustrated the morphological changes in the pristine wood substrate and the boron nitride nanosheet coating. Revealed surface grooves in the pristine wood substrate. Magnified images highlighted the irregular nature of grooves on the wood surface, providing a suitable foundation for the binder-free nanosheet coating. Magnified scanning electron microscopy (SEM) images provided a closer look at the complete coating formation of scanning electron microscopy nanosheets. The average thicknesses of nanosheets coated on wood substrates were determined using cross-sectional scanning electron microscopy (SEM) supporting information. Mesoscale surface morphology was investigated using scanning electron microscopy (SEM). Scanning electron microscopy (SEM) results, presented in Figure 3AF, illustrated the morphological changes in the pristine wood substrate and the BN nanosheet coating. Figure 3A revealed surface grooves in the pristine wood substrate. Magnified images, Figure 3BC, highlighted the irregular nature of grooves on the wood surface, providing a suitable foundation for the binder-free nanosheet coating. Figure 3D demonstrated the wood substrate after being coated with hexagonal boron nitride HBN nanosheets, showing a complete coating covering all grooves and forming a strong adhesion to the wood surface. Magnified SEM images, Figure 3EF, provided a closer look at the complete coating formation of boron nitride BN nanosheets. The average thicknesses of boron nitride BN nanosheets coated on wood substrates were determined using cross-sectional SEM, supporting information, Figure S3. Surface morphology and fire resistance of boron nitride BN nanosheets. High-resolution transmission electron microscopy HRTEM was employed to explore the surface morphology of exfoliated boron nitride nanosheets. Boron nitride nanosheets were visualized at low magnification in Figure 4AC, with average sizes ranging from 50 to 300 nm. Figure 4D presented the typical atomic structure of boron nitride BN nanosheets. The honeycomb structure of HBN with boron and nitrogen atoms covalently bonded was illustrated in Figure 4F. The selected area diffraction pattern, SAED, was shown in the inset of Figure 4F. Fire-resistant property of hexagonal boron nitride nanosheets. Fire-resistant experiments were conducted using a wood substrate coated with hexagonal boron nitride nanosheets as shown in Figure 5. Figure 5A highlighted the opaque white color of the wood substrate's coated portion, contrasting with the yellowish tint of the uncoated region. The uncoated portion easily burned, turned black, and suffered considerable damage after 60 seconds, Figure 5BC. Figures 5D demonstrated the fire-resistant characteristics of hexagonal boron nitride coating, remaining intact after 60 seconds. Figure 5F visually compared the wood substrate with and without hexagonal boron nitride nanosheet coating after a 1-minute fire experiment, showing the resilience of the hexagonal boron nitride-coated portions. Oxidation-resistant studies of hexagonal boron nitride nanosheet coating on wood. Oxidation resistance experiments were conducted at different temperatures. 300 degrees Celsius, 600 degrees Celsius, and 900 degrees Celsius. The experiments utilized a chemical vapor deposition (CVD) furnace system preheated to the specified temperatures. Hexagonal boron nitride-coated wood substrates were introduced to the heated zone, demonstrating oxidation resistance up to 900 degrees Celsius in air. No visible damage to the coating was observed at 200 degrees Celsius, Figure 6a. The evolution of small cracks in the coating occurred up to 600 degrees Celsius, Figure 6b. At 900 degrees Celsius, considerable morphological changes were observed as the hexagonal boron nitride coating withered and separated from the wooden substrate, Figure 6c. The dark tint color change in the opaque white HBN coating indicated the withering process, but no significant damage to the wood was observed at 900 degrees Celsius. Above 900 degrees Celsius, the coating withered out and carbonization commenced, Figure 60. The visible color change from opaque white to dark in the inset of Figure 60 illustrated mass loss and damage to the wood material. Up to 900 degrees Celsius, no visible mass losses were observed, but carbonization and considerable mass loss occurred beyond 900 degrees Celsius. These findings suggest that an appropriately thick hexagonal boron nitride (HBN) nanosheet coating has the potential to significantly enhance the oxidation resistance of wood materials at high temperatures and in oxygen-rich atmospheres. Mechanism of efficient wood protection by boron nitride coating. In plane thermal conductivity, hexagonal boron nitride (HBN) exhibits higher in-plane thermal conductivity compared to perpendicular conductivity, contributing to its anisotropic properties. Thermal diffusivity and effusivity. The poor thermal conductivity perpendicular to the planes results in lower thermal diffusivity and effusivity, as described by equations 1 and 2. Thermal diffusivity equation. 1. Alpha equals K divided by RCP, where A is thermal diffusivity, K is perpendicular thermal conductivity, R is density, and Cp is specific heat capacity of Bn. Effusivity equation. 2. E equals the square root of KRCP, where E is thermal effusivity. Anisotropic thermal conductivity. The anisotropic layered crystal structure of HBN leads to a significant difference between parallel and perpendicular thermal conductivity. Experimental thermal conductivity values. Standard basal plane thermal conductivity of hexagonal boron nitride is 390 watts per meter per Kelvin, while perpendicular C-axis thermal conductivity is only 2 watts per meter per Kelvin. Low thermal effusivity and diffusivity. The resulting low values, 4.83 times 10 to the power of -2 square meters per second and 9.1 watts per square root of meter Kelvin, respectively, indicate poor heat conduction perpendicular to the planes. Wood protection mechanism. The anisotropic thermal conductivity makes it difficult for heat to penetrate the coating perpendicularly, providing effective protection against combustion or oxidation. Coating strength studies, ASTM D3363 standards were employed to study the coating strength on wood substrates, supporting information figures S4 and S5. Stress, strain. Behavior. The stress-strain behavior of wood substrates before and after boron nitride coating was studied, revealing the efficacy of the coating, supporting information figure S6. Successful demonstration. Exfoliated hexagonal boron nitride nanosheets serve as a high-performance binder-free, fire-resistant coating for wood, demonstrating intact wood surfaces after exposure to fire. Oxidation resistance. The oxidation resistance property of hexagonal boron nitride wood coating was successfully demonstrated up to 900 degrees Celsius in air. Innovative use. The use of exfoliated boron nitride nanosheets as fire-resisting, oxidation-resistant wood coatings is reported for the first time. Thanks for watching.